Microsoft. And for those of you who listen to Jean-Philippe about the password hashing competition, this talk is of course of great importance to the community because you can easily do a password hashing competition, and there are several candidates in the competition. But as soon as we eventually pick up one or more candidates and say these are the recommended ones, we need the big companies to adopt them and say that we will implement these into our products. And basically, that's what I'm looking forward to hear from Marsh and Greg. So carry on, guys, and good luck.
Okay, thanks. Thanks, Per. So I'm Marsh. This is Greg. I work at Microsoft in Microsoft Azure. Greg works in Microsoft Research, where he's a cryptographer. Thanks, everyone, for coming. This is a big topic for me. I'm very interested in password security and authentication security. I worked for a startup company called Phone Factor, where we made a multi-factor authentication product. And I became involved in the PHC before we were acquired by Microsoft. So, Microsoft ended up getting into the PHC, maybe not entirely a conscious decision, but I think it's a good thing because I think we represent the industry in the PHC. I think JP's done a great job in getting a broad selection of cryptographers and attack side researchers and data security professionals on the PHC panel. But in terms of people who actually deploy the result of the PHC, we've got us from Microsoft, and I don't think that we have people from Google or Facebook or Twitter or the other big potential consumers of PHC. We have someone from NIST, which is equally important. So we would like for this to be as interactive a discussion as possible. If anyone wants to, we don't want to make this like a dry presentation of requirements. We would really like this to be a productive, back and forth engineering type discussion, where maybe we all learn something from each other. That said, we're here speaking as engineers who work for Microsoft. We're not speaking for Microsoft per se in that product direction sense. So we're going to be free about talking about what we want from a function, but at the same time, we're going to try to be real careful not to say anything that suggests that we're committing Microsoft to implement or ship or get behind any particular technology or function or any particular product. That said, if you think that something that I have said might indicate a particular product direction at Microsoft, our emails will be at the end of the slides, and feel free to get in contact with me, and I will try to direct any of your product questions to the right people. So what would Microsoft like from the password hashing competition? It's complicated. We went around the whole company, everybody we could find who was involved in developing applications, who was involved in network security, who was involved in product security, is involved in coding. We have a crypto board that oversees and reviews a lot of cryptographic choices. And I think that we're a large enough company that the responses that we got represent a good microcosm of the responses that the PHC is going to see when the winner is announced and we take this algorithm out into the world to kind of try to sell it. So what were some of the responses we got? Any kind of change is going to be traumatic for a very large organization that owns a whole lot of code. So we're going to get a lot more pushback than we are going to get wild, enthusiastic acceptance, and this is to be expected. But some of the responses that we got, just kind of paraphrasing an email, accuse us maybe of not being clear about what the threat model was here. We're big at threat modeling at Microsoft. Perhaps that we were kind of making fuzzy claims and shifting our position. There was a lot of response like, well, why are we even working on a new password hashing function? And there was some kind of acceptance. Well, if it comes for free, if it's easy to implement, then maybe there won't be a controversy. And a response we heard from multiple teams was, well, this is why we really need multi-factor authentication. That's the correct solution to problems with passwords. And the iterative hashing is like a legacy thing. And, you know, we all know passwords aren't going away, right? But this really gets to where I think the teaching moment is in this whole discussion is this discussion was predicated on if someone were able to build special hardware and get 3 orders of magnitude speed up. I mean, it doesn't matter what the rest of this email or this discussion were. It's all predicated on this question. Well, how much can an attacker with specialized, say, ASIC hardware speed up this particular function, make it more power efficient, more time efficient? And so this is one key result that we would really like to see from the password hashing competition is, you know, well, we have this PHC function, and we can actually say things about it in terms of, you know, we have a large degree of confidence that it will not be able, the attacker will not be able to compute this function 3 orders of magnitude more efficiently.
What you're saying is that a kind of mathematical proof would be a third party of Microsoft?
I wouldn't. Mathematical proofs are great, you know, but it's really just the fundamental security of this of the password hashing function revolves around the idea that the attacker will not be able to compute this function significantly more efficiently than the defender has.
From someone who's not really familiar with the field, say, as of mind, this is huge, and we know that.
Well, you know, I think that if you implemented a naive iteration of SHA-1 or something in a suboptimal scripting language, say, you might actually think that 3 orders of magnitude was, you know, a plausible speed up that the attacker might obtain. So, but perhaps the most common response we got was kind of like no response, just kind of crickets chirping. And this isn't bad. It's not, you know, a symptom of anything. It's just in any large corporation, not everybody's going to be able to respond with, you know, a well-reasoned and insightful response to every question that ends up in their inbox. So, you know, why does the password hashing competition exist? We need to start looking at how we address some of these questions because, you know, I think we all believe that it is doing something useful for the world. And I'm sure many of you have heard these types of questions. Why isn't salted hashing enough? Isn't PBKDF2 good enough? How will this affect our page load times and our application response times? We're really big on telemetry and automated testing and timing testing at Microsoft. Why don't you just use 2-factor auth? Why don't you just encrypt the hashes? Have you all heard this question before? Yeah. Why don't you just put them in an HSM or a TPM? And if the password file is compromised, you know, you're basically owned at that point. So why does hashing help? And we find these questions kind of are well-meaning, and they fall into these 2 categories. And the first set of categories, the first set of questions, we can answer with hard benchmark data. We find whenever we show like the benchmark results of, say, Hashcat OCL to someone who's not seen them before, they're really impressed, and and then they're at that point where they're willing to consider other alternatives. And then the second set of questions really relate to the architecture of the protected applications. And I think the best way to respond to those questions is with detailed threat modeling.
So, Greg, okay, yeah, I'll talk about this one. And I guess just to follow up on the previous stuff, it wasn't all bad. There were some, you know, positive responses that we got. We just chose to show some of the pushback we saw because we thought it would benefit the community.
Say the crypto board itself is really kind of watching with interest this whole process.
Yeah. So this is a slide, a diagram from a recent paper by Hurley, Florencio, and Van Oorschot, and I think it sort of explains the value of password hashing pretty well to someone who's maybe not totally familiar with this. So if you kind of walk down the decision tree, so there's a password file. It's only a problem if it leaks. And if the leak is detected, your system hopefully can force everyone to reset their password. So password hashing doesn't come into it there. So you haven't detected the leak, and you've salted and hashed your password file, so there's a potential for an offline attack. So this type of threat modeling, I think it helps get the message across to people. So when would you use this? And then on the subject of iterations, the same paper has this diagram which shows sort of how many guesses a password has to withstand. This is similar to the guessability metric we saw this morning from the CMU presenters. And this is something that some people can see and understand, that if you add password hashing with more iterations, then a weaker password needs to withstand fewer guesses to provide the same security. Okay, so here's sort of an outline of the rest of the talk. So we'll talk about sort of requirements, what we think we need from the PHC winner. And again, this is meant to be a discussion, so we're not in a position to dictate these to anyone. And then we'll talk about some things we think that could be picked up as work items by the community that would help get this deployed and in use. So Microsoft uses passwords in a lot of products, also in our infrastructure. I'll talk about some of our use cases next. And as Marsh said, we participate in the design review of features that use crypto, so we get to see, we get visibility into the process of choosing crypto and shipping it. We don't have a design in the competition, so we're kind of unbiased in that sense. Marsh is on the panel, the PHC panel, but this is not a communication from the panel. This is, as individuals. So, okay, what was the first version of Windows to use passwords for user accounts? Any guesses? Yeah, so it was NT 3.1.
We didn't bring a T-shirt or anything for you.
Sorry. But, passwords were showing up before that in Windows 3.11 for networking protocols. So the first use case, I'm going to try to go through these kind of quickly because I think they'll be familiar to most people. For online services, so this is when you're authenticating to a remote server, and the system will have hundreds of servers, or multiple servers anyways, each handling hundreds of requests per second. So this would be like browser-based logins, where page load times are very important. And we're also now seeing more logins from apps, right? Mobile apps, as well as browsers.
So this case includes the important cases of things like network file and print services, where you have protocols like SMB using NTLM. And, historically, these are very difficult to change because of third-party app compat reasons. A lot of cases, these passwords, these protocol formats got reverse engineered and deployed in compatible products before Microsoft ever publicly documented them. But there's this rich ecosystem of everything from SANs to VPNs and such that talk NTLM on some level. So it would be very difficult to change those types of credentials. But at the same time, we have to look at moving forward, at some point.
So the second use case is one you're all familiar with, logging into a device, a server, a laptop. So here, when compared to online services, you can probably afford to spend more cycles on your password hashing. One challenge is that usually, you set the parameters once and then it has to run on a large variety of hardware. So you don't want older or slower hardware to have a noticeable lag for the user, for example. The third use case is password-based encryption. So one product in particular is Office, where you can encrypt a Word document with a password. And this isn't really anyone's favorite way to protect data, but you use it when it's the only option available, right? And in terms of the attacks, this is kind of the worst case scenario because the attacker can start an offline attack as soon as he sees the ciphertext.
Can you tell us what function Microsoft is using for this?
Yeah, it's
all of them. I mean, we've done a lot to kind of migrate things over the years to more secure functions. But I mean, in general, I think newer stuff favors PBKDF2. And some is like using PBKDF2 with SHA-512. But as we mentioned, there's some stuff that we just can't change. Or it can only change if the client thinks that the server is at a specific protocol version or higher. Then the client is able to use stronger hashing. Question in the back?
Yeah. Can you say why, what scenario would this be the only option available? Surely the operating system would have some file encryption. Why would you ever need to go with a word processor?
Okay, so the question is why would this ever be the only option available? Why couldn't the operating system implement this encryption rather than having it rely on the word processor in the document format?
it comes down to key management, I think. So if I'm sending you a document over email and we haven't exchanged keys, then the password may be the only option we have to protect the document. It's also, I think, for low-value documents, people are comfortable with passwords, and they like it, they use it.
Yeah, so I think document exchange is the real answer. You might take this document from one computer, send it to another computer, and those systems have no prior relationship whatsoever, except that the document was exchanged, and they both support this common file format, which defines a form of encryption. And this is kind of a worst case scenario because the attacker gets all the ciphertext, gets all the plain text. It's equivalent to him like pwning the server and getting the password file. He can mount offline attacks. He can parallelize them as much as he wants. So if we can solve this scenario where the attacker also has his own like ASIC foundry, then probably all the other cases will come along.
We're in pretty good shape, yeah. Okay, so that was it for use cases. I guess I just wanted to ask whether the audience thinks we missed any major use cases. Most things kind of fall into these three buckets in terms of use cases that I've seen, but let me know if there's one that you think we've missed.
Like encrypted chat protocols or pre-shared key protocols or was the TLS
like SRP
and
PIC
type stuff.
It's sort of abuse, but for better or for worse, we're also seeing crypto companies using a lot of password hashing-based schemes for some sense of security.
Yeah.
It has nothing to do with protecting people's passwords, but they're trying to take some security from password protection and sort of coerce it into security for coin generation or some other cryptocurrency type thing. So we should really think of a function that makes sure that it's not going to be your code being used for something other than passwords.
Yeah.
Right.
Yeah, it's a generalized proof of work.
We can do another competition there.
Yeah. Well, I think that's already started.
Cryptocurrency.
Right? You got Bitcoin, you got Dogecoin, you got altcoin.
Generally with this, I remember when the project started, we talked about whether this is going to be password hashing or also key derivation.
Mm-hmm.
And chances are that it would be usable for key derivation, but there was a conscious decision to not state that as a requirement. So we could focus on that. I mean, I'm obviously going to use key derivation.
Yeah. And Microsoft, we were saying we would like key derivation as well. Key derivation is an important scenario for us.
Yeah. And I think that's one of our requirements. So we'll have a slide about key derivation.
So could you go back to the Dilbert? So this is like a Dilbert panel. This is the last one, and he's like, well, we need to get requirements from all these engineering teams, but I can't, like beat them out of things. So, right? So we couldn't go around the company with a stick and like beat engineers until they gave us real requirements. But in practice, that's not really a productive technique anyway. Password hashing is sort of a very password hashing is sort of a very specialized field, and it's unlikely you're going to be able to get generalist developers or developers who are specialists in some other area to articulate exactly what they need. The best we can do is make something, that we think that they need.
Okay, so yeah, our requirements are kind of over and above what the call for submissions required. They're not deep technical requirements, so we'll save those for round 2 when there are fewer candidates and we can spend more time with each one. So really it's just, as users of the PHC winner, what features would we want it to have? Right? So these are driven mostly by use cases and some of the design trade-offs that you have to make when designing a password hashing function. So the first requirement is that we'd love to have only one winner rather than one per use case. So this makes it easier to tell to help product teams use it safely and securely. It's easier to deploy it, and with any change, it's hard, right? So having just one function, we think will be easier to have it adopted.
And so when we say easier to give guidance to product teams, if you haven't worked at a company with tens of thousands of engineers, you might not appreciate that little sentence literally means going around and talking to 10,000 engineers to give this guidance. So simpler is better. It's going to be, it just has a higher chance of being more widely deployed.
Okay, and so we mentioned PBKDF2, that it's being used currently. It's kind of a de facto standard.
I think it's an official RFC
standard. Right, but okay.
But I think because it's the most standardized, PBKDF, except for PBKDF1, which we don't speak of anymore for certain reasons, it is the gold standard right now, for better or worse. Now, it takes a really enlightened group like a BSD or a TarSnap or something to actually decide that they need different requirements than this.
Right. So we'd like some amount of agility between the new function and PBKDF2. So in order to get this, the security guarantees should be the same or better. You should be able to use it for key derivation. And then that sort of forces the variable length inputs and outputs, right? For key derivation, you always often have additional input, and you also usually need a variable amount of key material, so the PHC winner should let us specify those.
So you mean that ideally the winner should have the same API as PBKDF2 with the same parameters and the same range of parameters?
Yeah,
to directly replace.
Support the same range, and then it'll have the memory parameter, which will be new. But
well, I think is it the next slide? I think we can talk about it in a little more detail. Yeah.
Okay.
So what we would really like, can you go on? So we want a clear migration path for engineers. I don't know that it necessarily has to be the exact same API parameters, but we want a document that says, if you're an existing user of PBKDF2 and you're using it with these parameters, then here's how you could map those parameters. And a document or guidance like this is what will enable an engineer to, who's not necessarily the world's expert in password hashing, he can take this document and say, here I have justification for migrating from something that is, an RFC standard to the PHC result.
Okay. So the next requirement is driven by our need to support various hardware, right? So the design shouldn't be kind of overfit to a particular processor feature that isn't widely available. AES-NI is sort of the best example there because it's not available on ARM. The defender may have these processor features, but the attacker certainly will if he wants them, right? So it introduces an asymmetry. So one way you can realize this is by making black box use of existing primitives, right? We already have optimized implementations for all the platforms we care about, so we don't have to do any new assembly language implementations. And this also solves the problem of implementing this in high-level languages, right? In C#, we can call down to the platform crypto, but if we had to implement the PHC winner directly in C#, the performance would be a lot worse. Right? JavaScript is another one, and it might not be a need now to do password hashing in JavaScript, but given enough time, someone will want to do anything in JavaScript, right? It just seems to be the way things are going.
So we would really like a well-defined API for developers. Obviously we have to have a C-compatible API, but we also want it to map to high-level languages easily as well. We can't ask that it be foolproof, but maybe it can be as fool-resistant as is practical. And when we say API, or when we want one winner function, this API could reasonably be two functions. One where we take the canonical password and the parameters and derive a string, which then is the authentication credentials that might be stored in, say, etc shadow. And then a separate function where we take a candidate password guess, or a login attempt, and the stored credential string, and then return a Boolean thumbs up or thumbs down. This is or is not the valid password for this particular string. And a key feature of this is that the string should encode all the metadata, all the parameter choices in its output. Now I know some formats like etc password already have a separate field for iteration count and things like that. But in my experience, and I've actually seen this in that it's a whole lot simpler, and it's a whole lot more likely that developers will get this right if we're not asking them to store separate database columns for iteration count and for salt and for the algorithm used and for any other optional parameters that might come along. If the PHC can do one thing really good, it would be defining this mapping of the PHC function to a credential format string that's probably base 64 or something like that, that then can be stored as the credentials and save developers from the work of, even if you just ask people to add one more database column, a certain percentage of them are going to have trouble with that. And this is also very important for another reason. We want to provide good conservative defaults to these parameters. We want to set developers up to win with this thing. And choosing the correct iteration count and the correct values for all these problems is a hard problem, and we shouldn't just kind of push that off onto developers because we ourselves in this room don't always know in advance what the correct choices will be. So we want the API to have default values for these parameters, and just as importantly, we want these defaults not to be set in stone, but we want them to be able to evolve over time with increasing CPU capacity, increasing attack capacity. And a key for the ability to evolve these defaults over time is that the metadata gets encoded into the credential string. Because if we didn't do that, then developers would write code that would break as soon as you change these defaults, because it would work one day, then we change the defaults, it would break.
Okay, moving on. So side channel attacks, there's been some discussion on the list as to whether you should have protections against side channel attacks. So we think there should be. It should be a design goal because of the broad range of use cases, and also, the systems where you're doing the hashing. On some systems you may have this side channel leakage, on others you might not. So it's best to just protect against it. And given the long life of crypto functions, we'll see new use cases emerge that may have problems with side channels. So there are two large classes of side channels: the timing attacks. This is where, as the input varies, you have a different runtime. So it seems that most candidates can be implemented in constant time without too much trouble. So I don't think this is a big issue. The other one is cache timing attacks, and this is where the victim and the attacker are sharing a cache, and the attacker accesses things in his cache and records the time, and then learns information about which memory items the victim accessed.
But that would never be a problem in practice, right, Greg? Why would a defender ever let an attacker share a cache with him?
So yeah, that's as a cloud service provider with virtualization, this is.
There have been lab-level proofs of concept of people attacking each other from one virtual machine to another because the two happen to run on the same hardware and share the cache. So it can happen from someone else, another customer for the same from same cloud provider.
Yeah.
And it's becoming more and more common. You cannot control that.
I think.
Yeah, we don't want to have to assume that each customer is running on sort of separated,
Well,
isolated
another way
hardware.
to say that is multi-tenancy is sort of the cloud industry buzzword, right? It's like there are massive economic advantages that are gained if you allow multiple parties on the same shared hardware. So PHC result really ought to be compatible with that, we feel.
So I think there's some nuance to cache timing attacks that don't really usually get captured in short descriptions of them.
Well, to that point, we had some more slides about like cache timing attacks, and we kind of dropped them because we figured we would be running low on time.
Yeah, okay.
What?
I'll show up then.
No, I wasn't. I'm not saying that. I'm just saying that's like a really fascinating discussion, and maybe we can like have time for Q&A for that.
Okay. So I will say, just make a brief point about the countermeasures. So, there are countermeasures to most types of side channels, implementation countermeasures, and these make the defender's implementation slower, and the attacker can simply ignore them, right? So that's why I think it should be sort of a part of the design, not left to the implementer. So on cache timing attacks, the PHC candidates, I'd say roughly half of them have some kind of password-dependent memory access. And I mean, they all do one of these three things, right? The memory access is independent of the password, or it depends on the password kind of completely. And in the third case, you have sort of a mix of the two where you do some amount of work and then you access memory in a password-dependent way. So I'm not sure, which is the best approach. I think the third one needs some more analysis.
Well, I think approach 2 kind of falls apart pretty quickly if you assume that the attacker has some visibility into the password, because the passwords tend to have such low entropy. The goal of this function is to protect the lower entropy range of these passwords as much as is practical. And if you start doing memory accesses that depend only on a low entropy password, then the bad guy really only needs to observe like 2 or 3 memory accesses before the whole password falls apart. So I would consider technique number 2 is kind of the non-starter.
Yeah, so but between 1 and 3, there's room for discussion, I think. So this next requirement, we have some arguments in favor and sort of against it. And this is to be agile in the choice of primitives. And here I mean the primitives that you use to implement your password hashing function.
So we have a crypto board, we have a company initiative to bring agility to our choice of primitives.
Right. So for instance, HMAC has this type of agility. You can change the underlying hash function. And so this can help with formal security analysis. You can make assumptions about well-studied primitives that may be unreasonable of a function that hasn't been as well studied. And then some designs use reduced round variants of primitives, and this I think should be optional, not required. And so here's why. So this is sort of the space of parameters, the time and memory parameters, and so with a standard primitive, you can hit, that's the green line, you can hit anything above that line, right? And then if you go to, so standard here may be like SHA-2, right? And then a fast primitive may be like Blake2B, and then you can go to a reduced round primitive, which is even faster, but then you're not going to beat memset, right? So these parameter choices kind of fall into 4 quadrants. The 3 that are in white can be hit with a standard primitive somewhat, and then there's this sort of quadrant of death where you want to use a ton of memory in a very short amount of time. And this is where you really need a reduced round primitive or a less standard primitive, right? So I think that by having flexibility in the underlying primitive, you give the choice, right? If your application needs those parameters, you can use a reduced round variant. But if you don't, then you can use a different internal algorithm. And yeah, sort of as an aside, the security properties that these reduced round variants actually need for secure password hashing is underspecified. I think it's kind of vague, and it has to be somewhat unpredictable, but I haven't seen too much formalization there. So now, yeah, so there were some other points here.
So, I mean, a whole other way to look at this is, do we really want, if we're asking for agility in these underlying primitives, I mean, it's almost equivalent to asking that it be composed of standard primitives, which sounds like a reasonable thing to want, but we should look at it more closely. I mean, has there ever been a case where, primitive agility made a difference in a password hashing function? We have some experience where we had a format that was based on PBKDF2 SHA-1, and it was being cracked too efficiently, and we upgraded the format to PBKDF2 SHA-512.
You mean HMAC SHA?
Yeah, with HMAC. Yeah. And so this had a great effect on the strength of the password credential storage algorithm, but it was really, I suspect that the effect that it had related to the difficulty of fitting SHA-512 in a GPU, as opposed to any kind of algorithmic weakness in SHA-1. So this could be a case that would be cited where algorithm agility might be valuable, but really it's just a poor man's knob for memory hardness, right? Yeah. I would say this is an unstated requirement, but we would really like not to see those MD5 constants anywhere in our source code, because we grep for that stuff, and it's just annoying. It kind of makes the analysis difficult, right? If you substitute one of these primitives, does it make a new hash function, or is it really the same password hashing function with a different parameter? How much of the security is being violated? And are we really going to go down the road of trying to prove this kind of equivalence every time anybody wants to substitute a different underlying primitive inside the thing? And on the bigger point is, we really want the benefit of the opinions that are going into the PHC to show up in the resulting function, and we don't want to put developers in the position of having to choose a secure primitive to use with their password hashing competition framework for generating password hashing functions. We really just want a password hashing function with the correct knobs and dials needed for the defender to tune it to his defender hardware and his application requirements. Question?
Well, for a small comment, so we just, from the security point of view, we just started cryptanalysis of this PHC candidate, and regarding memory hardness, it's not really clear that you need any sort of secure crypto primitive within the hash function. I mean, as secure as it would be needed for most operation. But for memory hardness, it's really unclear if one round of AES is, in some sense, worse than 10 rounds of AES.
Yeah.
It's really underexplored, and requiring these functions to use the full strength primitive can be like lower killed.
Mhm.
Serious ones like 10 times penalty.
Yeah.
So the observation is that it kind of depends on the algorithm and the analysis whether or not it relies on certain security properties of the standard primitive in order for its own security. So I mean, one interesting case of password hashing functions is they tend to be very generous with the amount of CPU time. I mean, they're in fact trying to burn CPU time, and so they have a generous safety margin in case it's not like AES, a block cipher or a stream cipher where you're trying to get down to single cycles per byte of data, right? Here we're trying to throw as much computation as possible. So I mean, famous last words for anyone in crypto, but maybe it's not the end of the world if it's built on a primitive that isn't perfectly secure on its own because it's going to be run in thousands of iterations.
Like MD5.
Exactly like MD5. Yeah, seriously, is PBKDF2 HMAC MD5, is that broken in any way that it's supposed to work over 100 iterations? I don't think so.
But I think if you have work in this area, make it known. I think it's important.
Unfortunately, I had to skip the first part of the talk while giving the presentation of the project.
Yeah.
Oh yeah.
No, this is right on topic for I hope you're on the PhD mailing list and bringing this research out. So.
But that previous slide actually illustrates the problems with false agility. In that with SHA-1 and 2, you didn't say HMAC. While you don't actually need the HMAC for SHA-3. The same is I see the developer not knowing that they needed to make it HMAC SHA-2, especially in light of the fact that they just use SHA-3 without it.
Okay, so what you're saying is there's an excessive abbreviation in my slides, or maybe a typo in my slides, which illustrates why agility could introduce errors.
That's exactly what I'm saying. Yes.
I think what Jeff's saying is that unlike for SHA-2, for SHA-3, which is not standardized, you can use it as a MAC, what as a keyed mode of operation, and this mode is not specified for SHA-2. But it's unclear whether NIST will specify this keyed mode when they release SHA-3 standard.
I think they said they would.
They will? All right.
Yeah.
Will be good.
I thought that HMAC MD5 under SSH
HMAC MD5 under SSH. Okay.
supplemented SSH already.
I'm guessing that relates to the message layer of the SSH protocol and not HMAC MD5 used as a component in an iterative fashion as a password hashing algorithm. Good. Perhaps?
There's been some attacks on NMAC MD5. Not sure if there's been an attack on HMAC MD5. I don't think so, but
There's-
yeah.
Are they beyond early spawn?
Maybe.
Okay, so do we even want standard primitives? Most or all these standard primitives, they were intentionally designed to be more efficient on ASICs than typical general purpose computers. And this is the opposite of what we want in a password hashing function. The PhD is developing a different and newly identified type of primitive, right? It needs new properties that were not present in the design of AES or SHA-3 even. So, let's not constrain it out of the box to be built on top of standard primitives that might actually be inappropriate, simply because they're standard. So if the PhD doesn't actually require standard primitives, then do we even need underlying standard primitive agility? It's a good question. I don't know.
Okay.
So I think we're running under time pressure. So this is a good time to start interrupting us more, and we'll just kind of ease our way into Q&A.
Will you talk about the features like server relief, hashing upgrade in this part? Or? Otherwise, I'm asking the question.
Yeah, we didn't have any content on. So server relief is when you ask the client to do some of the hashing. Did we consider that? Do we have the?
Sometimes we didn't directly address the server relief concept. Well, the concept of server relief, where, say a JavaScript implementation that's running in a web browser, the web browser could take the user's low entropy password and, say the server provides it with a salt of some form, and then the browser does some of the work up front to convert this from a low entropy password to a partially hashed, like intermediate form, and then the server gets this and maybe does some more hashing on it before storing that in its credentials. This allows the server to offload a bit of this expensive computation onto the browser. And there are some pros and cons with it, but we're saying do some of the work on the client side. And we're not proposing this. We're just saying this is an idea that is often tossed around. Huh? We're not proposing. This is not our idea. We're not proposing it, but it is an idea that people often raise. And so, for the PHC, the question keeps coming up, and we didn't have a slide about it.
I think there's actually going to be talks specifically on that.
Yeah.
The mantra for web security is keep it off the client. So
Yeah.
for you to come out and say the opposite.
I didn't come out and say the opposite.
Yeah, no.
I said that some people, this is a question that is consistently being raised.
Yeah, the way I'm asking the question is that many of the PHC submissions support these features. So the question, do we see it as clear advantages or just nice to have or useless? I don't know.
I don't think anybody would argue that there's a lot of untapped potential power out there. That's what we put it. If clients are picking up more load, there's a lot more of them than any of us would ever have. Got it.
Yeah.
But that also is exactly the way that the attackers are doing that out of the face.
Yep.
Give me any vector of having control over how to sync the equipment.
Well, so, if the attacker's on the client machine, he gets the password in the clear. So,
Yeah, I think when you lay out the threat model appropriately, and some of the concerns actually know that.
yeah,
It's a threat
it could
model
make
discussion.
sense. Sometimes, yeah.
Yeah.
So how much time do we have? And do we want to?
We have 10 minutes.
10 minutes.
We
Okay.
have 10 minutes, and then there's a 10-minute break. So
Okay.
Okay.
So we'll kind of run quickly here and then get to some more Q&A, and then we'll be around on break.
Okay. So I took some of these requirements and put the candidates in a table to sort of see which ones meet the requirements, which ones might meet the requirements, and which ones don't. So yeah, this is my individual opinion. This has nothing to do with the PHC panel selection. So here's what I came up with. So the first two have to do with the KDF, whether it's a secure KDF, whether you have flexibility in the parameters for the second one. The third one is, whether it's tied to a specific CPU architecture. The fourth one is agility, if you can switch out the underlying primitives. Then we have side channel resistance and whether it supports all of our use cases. So there's the table. I'll sort of summarize it as, so Katana, Gambit, Makwa, and Rig meet all the requirements clearly. Libra2 and Pufferfish mostly meet the requirements. Two candidates are missing only the side channel requirement. That's Lanarea and YesCrypt. And BadCrypt and Centrifuge meet the use case requirement, but not some of the other requirements. So we could use them, but they may not have all the features. And I'll point out that probably tweaks would change the table and change the list. Because, for instance, the KDF ones, I think are pretty easy to add to a design with a tweak. So.
It's interesting that the two of you were moving towards Lyra as a commonality.
Sorry, which two?
He just did a talk talking about basically memory usage and how well it is. You're bringing up Lyra here as a process standards here. Just bringing up commonalities.
Yeah, so Lyra 2 you mean for side channel resistance? Or okay. Okay, so we have a few things that the PHC community could kind of pick up as work items that would help this technology get deployed. So the first one is guidance on parameter selections. So with other crypto primitives, NIST and others have made similar tables to this. So this reads that if you need security beyond 2030, you need RSA 4096, not RSA 2048. And I don't know of an equivalent table for password hashing. So some of the research that went into tables like this, sort of two things that they need are existing data points and explicitly formulated hypotheses. So for password hashing, we have some existing data points. So there's benchmarks. We mentioned earlier how this sort of helps people understand the problem and it helps them choose their parameters. But these benchmarks maybe not realistic for what the attacker is actually doing, right? It's kind of on PC-like hardware, and we don't know what the attacker is using. So maybe we want to have an organized way of collecting benchmarks, something similar to the EBAX project, where you can submit code and it gets run on a whole bunch of hardware.
So instead of taking days to run, it will take years. Let's test the 1 gigabyte to.
Yeah. Right. So, but if we do decide that we need more benchmarks, what hardware should we run it on? To best model the attacker, and what should we benchmark, and how do you get people to participate? Because if you're an attacker, you may not have an incentive to tell the world how good you are at attacking these things. For
use something literally just thinking out of the box here, but use something akin to Bitcoin and how they're basically it's just kind of hashes, right?
Yeah.
And everybody's in a big hurry to show what they're doing there. So if you bring that type of
there's kind of a natural incentive there too.
Right.
Yeah.
So the question is, can you use something like Bitcoin to provide the natural incentive to publish benchmarks and
specifics would be that there's a model there that
Yeah.
everybody's more than willing to say, hey, look how good I am.
Yeah.
That's an interesting idea.
Yeah, cool idea.
So I know you're short on time, and I don't want to sidetrack too much, but I think that the focus or the emphasis on benchmarks is possibly misguided. And the reason I say that is because almost every proposal has a time parameter and memory parameter, where you can make it go as fast as you want to as slow as you want. It's pretty easy to waste memory, it's pretty easy to waste CPU. So we need to, if we're going to look at benchmarks, how do we really compare apples to apples versus apples to oranges? We need to do things like compare, how much time does it take at this memory parameter? How much time does it take at this memory parameter? That sort of thing. There's a little more nuance to it than
Yeah.
that's what he did.
The problem is that apart from time and memory parameters, what can this have 5 other parameters?
Well, and even to take this further, it has to be like a competitive benchmark game, right?
Yeah,
We have to show that nobody can run it faster than this, not just what a naive implementation might run it at.
The Bitcoin parameters and benchmarks are real world. It's what people are actually doing and showing. And by the way, every time they get a Bitcoin, they're like, here's what they did. So the point is, it's real world. So it's actually straight on with what they're asking.
So what we all need to do is like buy a bunch of Bitcoin and password protect them and put them on Pastebin.
Yeah. So this would be just like a crypto like the RSA challenges, right? Here's a number, factor it, and we'll give you $1 million.
Well, actually, if you could make it an
Microsoft did not say we're giving those dollars.
the amount of time and effort that it would take them to create, to do a Bitcoin calculation compared to the time and effort it would take to do whatever algorithm you wanted to look at, and then you do a rough equivalency out to whatever you're looking at.
So Bitcoin has been to layer 2 and Bitcoin.
Sorry, which coin?
There's a coin called Bitcoin.
Bitcoin?
Like a GPU something.
Okay.
And they've announced a few days ago that they're going to move to layer 2 sometime like in December.
Could you post a link to the PHC mailing list so that we?
Yeah, sure.
Thank you.
You see what I'm saying? If you can find an equivalency, then you would be able to very quickly and easily have a real world, here's what you would expect here.
Yeah.
Wouldn't be precise, it wouldn't be the most precise thing, but it'd be damn close compared to what you got right
Yeah. Well, I think this has proven extremely useful. Data breaches have proven extremely useful to the field of password security research. And we're essentially talking about backing it with cryptocurrency. So let's keep moving here.
Okay. So for explicitly formulated hypotheses in the public key crypto setting, these are like, you can count on Moore's law, improvements in networking and memory, and some algorithmic advances, but for password hashing, like what are the equivalent things that you would need when giving parameter guidance? So you'd have to have some idea of what hardware the attacker would use and how those resources would change over time.
Yeah. We need to start brainstorming, like, what are the new attacks that we will see coming down the pipe in the next 5 to 10 years?
Quantum computers.
Huh?
Quantum computers.
Well, hopefully quantum computers is a way out, but what about are some major cloud providers going to do FPGAs as a service, right? What if the cost of developing ASICs drops dramatically, because of, Osh Park gets into the ASIC business or something like that? These are known unknowns that we probably could predict if we really put our heads together, and so we need to start thinking about that as part of the PHC discussion.
I think, we can probably wrap it up here.
Okay.
So we're out of time, I guess, or there's 1 minute maybe.
So there's a break here that we can steal for Q&A unless you leave the room, in which case, thank you all very much for coming to our talk.
Yeah.